the Dynamical Systems tutorial. What are we going to do today? So I hope that we can answer the question, what makes a system dynamic? And you will see some basic math for describing and also analyzing dynamical systems. But we will more focus on conceptual understanding. So I will show you equations, because those of you who are skilled in math, trained in math, for you, then it's easy to grasp what those equations are standing for, right? But if this is not familiar to you, then it's not a problem. So just focus on conceptual understanding, which is just as powerful as mathematical equations, if you're a little bit trained on this. And then we will talk about stability, and if there's enough time, probably we also cover bifurcations. And those 2 points probably are also new for those of you coming from an engineering or physics also background. Yeah, so this maybe is a review for you, and if this is the case, just lean back and enjoy. And if not, then try to follow me, ask questions anytime. So this is really for you. Good. So starting with a dynamical system, I put a quote here from Edward Scheinemann, who wrote a book, Invitation to Dynamical Systems. And his quote is, "A dynamical system is a function with an attitude." And I put this quote here because his book is free, so you can find it, I guess, on his webpage or GitHub page or so. It's a really nice book for like beginning to think about dynamical systems. And if there's something unclear today and it's all really unclear to you, maybe it's worth to take a look at this book. Okay. So when we have a dynamical system, we have variables, or we also call it state. And this state somehow changes over time. And we denote this as a function x that varies over time t, right? And we also have a rule or function that describes how the state evolves with time. So, and usually this is a function of the state itself. So it's f of x, and x then varies with the time. And dynamical systems are kind of the universal language of science. You find them in physics, in engineering, chemistry, biology, economics, and so on and so forth. And today I will show you a few examples which I think are from basic physics. But maybe they give you an idea that you encounter dynamical systems basically every day. Okay, this should be a recap from school about time variation and the rate of change. So when we have a state like x, and it varies over time, we have a rate of change. So this is the time derivative of x. So we often denote this as dx dt. Maybe from school it's kind of x dot or something like that. And yeah, one example, of course, is that the state of variable is your position in space, and your rate of change is the velocity. So yeah, so the velocity gives you like how your position changes with time, right? And also we can take the rate of change of the velocity, which is here's a question mark. So maybe some of you is willing to give an answer. What is the rate of change of the velocity? So in the chat, yes, exactly. So the acceleration. So when you're sitting in your car and you're pressing like the gas pedal, you're not only changing your position in space, but you're also changing how fast you go, right? So then your car is accelerating. So this is kind of the math language. So you have a variable x and t and this dx dt, but we can also, for our conceptual understanding, take a look at these plots. And this is again, so the position x in space and the time t. And this, we call this trajectory in space, or the time course of x, gives me at which time point I'm at which position in space and how far this is away from my initial condition, which was probably 0. And when we take the derivative of this function, we get the velocity, so the rate of change, which is the slope of my position in space at every time. So here the function is steeper than here. So apparently my rate of change increases over time. So this is exactly what is covered here by this linear function. And this should be also known from school. So this apparently is a quadratic function, and this is why we have a linear function as the time derivative, right? So if this is not clear, maybe think about this until the next week, because the understanding how these two plots are connected is really important for this course. Good. So the next thing would be when we have now the velocity as a time course, and we want to know its rate of change. So which kind of function would we get now if we take the derivative of a linear function? Again, a question you may answer.
The acceleration?
Yes, so it's acceleration, but how would the function look like over time?
It's like a constant slope.
Yeah, so exactly. So the slope of this linear function does not vary over time like the position here does. So we would have a constant function. Maybe I can annotate here the screen. I'm not sure. Maybe. Yes, so we would have like a constant function. Maybe not at 10 meters per second square, but you know what I mean, right? So we would have a constant acceleration over time. So which is, as Julian wrote in the chat, a linear function as well, but kind of without a slope. Okay, good. Okay, now okay. Good. So I already said that we call this trajectory or time course of a dynamic variable, and then we have the rate of change, which is the slope of the trajectory. And here's another example. So we have the trajectory of the state, which is now called U, and how it varies over time. And now it's not increasing like in this example, but decreasing over time. And this is why our derivative now is negative, right? So the state always decreases, so we have a negative derivative over time. And when we talk about dynamical systems, we often talk about the relationship between such a state and its rate of change. So the function I already mentioned, that the rate of change is defined by a function of the state itself. And here we have the time courses of the state and its derivative. And on the right-hand side, you can see a phase plot of the dynamics. So where we have exactly this picture of how the rate of change depends on the state U. And we can now derive this phase plot from those two time courses by eliminating the time. So we take a look at the time point where we have here this star value for the state and its derivative. And then maybe I can use the annotation again. So at this time point, we have this value of u, right? Well, so, and this is what we find here. Good. And in another color, at the same time point, we have this value of the derivative, right? And this is what we have here. So, and at the star point, we have a larger derivative and a larger state variable than we have here at the square part. So, okay. Is this clear? I hope so. Or are there any questions? Because this is also really fundamental that we know what the time course is and the phase plot. Okay. Good. Then the annotation. So with this in mind, so knowing what the time course is and what the phase plot is, we can start to talk about linear dynamical systems. Sorry. So this is what we've already seen. So we have now again a state x and a linear function. And here also this variable b is 0, right? So, sorry, we have this, linear dynamical system. And it's not always true that we already know the solution, right? Like here, but we often only know the dynamical system and try to find out what the solution is. Okay, so and when we want to find this solution, there are two ways, maybe more. The first is guessing, and the second is calculating. And guessing here means that we know that a function, so x, whose derivative dx dt is kind of the function itself, but with some factor. So we have this tau here and this minus here. So a function whose derivative is a function itself, but with some factor. And you probably know that this is true for the exponential functions, so e to t, and this is what we have here. So our solution probably is x of t is the initial condition x of 0 times the exponential function of minus t over tau. And this is where this minus tau factor comes from. So you can also calculate this, and you can try this on our exercise sheet, which is about dynamical systems, and you can hand it in next week. So we will put it on the web page today. So for now, you can just maybe in your mind verify that this indeed is a solution to the linear differential equation by differentiating it with respect to t. So we get the exponential function itself, right? And then with the factor minus 1 over t, and this is what we can find exactly here. So if this is too fast, maybe just try it out with a pen and paper by yourself. Okay. And this is a plot now of the exponential function, which is decaying. So we have the phase plot here of the dynamical system, and this is the solution, the time course of x of t again. So and what you see is that the state decays over time, right? So it decays to 0. And we call this exponential relaxation to an attractor. And we will see, yeah, in the next slides, what an attractor is. And then we have the time scale tau. So tau is the time at which these initial conditions, so this x0, is reduced to x0 over e. And yeah, so this is what characterizes the exponential relaxation to 0 here. And the same applies, maybe I used this again. So we have here the time point tau, and then we have x0 over e, and at the time point 2 tau, we would have like x, well, 0, no, this maybe is not a good idea. So it just decays over e again. So we would have x0 over e square at time 2 tau. So this applies to any other time point t. And this is also something we ask you to examine on the exercise sheet. Okay. So maybe this word attractor, you can yeah, have it in mind, and we will talk about this later. Okay, so now a dynamic system is usually not linear, but we have kind of a non-linear function. So, and again, this is now a phase plot. So where we have, again, our state here and our rate of change here. But now it's a non-linear function and not a linear one. So we may have any function of f that describes our rate of change. And what's important now, or what's so great about dynamic systems is that when we know the present state, so something like an initial condition, we can predict the future, and we also know the past of the system when we know the rule f. So we do not necessarily need to know the solution of this differential equation, but it's sufficient to know this rule, so how the rate of change behaves. And this is what we often call mental simulation, and we will ask you to do such a mental simulation on the exercise sheet as well. So this works by taking a look at the initial conditions, so this blue value of the state. And when we know the initial condition, we also know the derivative, so we know how the system will change with increasing time. So here the derivative is negative, maybe a small negative value. So we know that in the future, the initial condition, in the future, the state will be driven towards negative values. So this is what the green arrow indicates. And maybe when we measure the system at some discrete time points and we measure it at the next time point, we have a new condition, which is maybe here. And then again, we can read out the time derivative and see, oh, well, it's going to negative values again. And then you can do this again and again. So maybe your initial condition was here, and then your time derivative was positive, and then you would be driven in the opposite direction, right? So a state with a positive time derivative is driven towards higher values. A state with a negative time derivative is driven towards lower values. Okay, then a question for you. What happens exactly here? So, yeah, any idea? Yes, Simon.
Yeah, there it's stable and it stays in that state.
Exactly. And why it's stable there?
Because there's no rate of change at that point.
Good. Yeah. So because your rate of change is 0, the system is not going to change in any direction and it simply stays there. Makes sense, right? So yeah, this is what we would call fixed point, and we are going to talk about this later. Good. So this is kind of the conceptual mental simulation you can do, and this is kind of the math equivalent. So when we take a look at this differential equation, we have again the state x, and if it's not a scalar, we call it state space because it can also be vector valued. It can even be function valued, which is kind of more weird than vector valued. So we will take a look at vector valued state space later. And then we have again our rule, which is the dynamics of x. And if we have vector valued x, it's also called a vector field. And then we have the solution. Yeah, and the solution is always a solution with the initial condition in mind. So kind of you need to know where to start to get the correct trajectory in your state space. Okay, and this solution then obeys this differential equation. Good. So I already hinted at it, there are different forms of such dynamical systems, and we already analyzed a linear dynamical system, which was one-dimensional, so there was only one scalar variable, and this can be nicely illustrated using these plots. And so these are ordinary differential equations, just for those of you who are familiar with this. And yeah, then we have this initial value that determines the future. So we may also have vector valued differential equations. And then the initial state is not only one value, but more than one values which we can group together to such a vector. And then we get a system of differential equations, which we can also group together by this function f. And yeah, I think I have an example. Yes, exactly. So when you have an engineering system, then you can think about this entries x1, x2, and so on in your state vector as being all the quantities that you can measure in your system. Okay. So an example from simple physics, basic physics, is the ideal spring. And we call it ideal spring because we say there's no friction. And it's also ideal because it obeys Hooke's law, and you have to believe me that there's something like Hooke's law. So this is a spring and a mass connected to it, and then you displace it a little bit by this, displacement x. So this dotted line is where the spring likes to live, so where it's in equilibrium, but if you displace it, it will probably bounce back and forth, right? Going to oscillate. And yeah, what you can now measure is the velocity and the position of the spring, right? And we know that there's something called Hooke's law, which says that the acceleration, so the rate of change of the velocity, equals something that is defined by the spring, which is the k, and the mass, which is the m, times the displacement x. Just believe me that this is true. And we also know that the rate of change of the position is the velocity, right? So this is easy. And now we can write the equation. So our x dot equals f of x with two vectors and a matrix. So our position x and our velocity v is now our states vector. And here we have the time derivative of x and v. And this is the matrix being the function f. And we can read this out by saying x dot equals 0 times x, okay, and 1 times v, which is what's standing here, and our rate of change, so our acceleration equals minus k over m times x, which is Hooke's law, and it does not depend on the velocity. So this is simple matrix multiplication, right? But this is how we can nicely write those two differential equations into one system. And yeah, then we can also solve it. And again, you may want to verify that this is the solution, so that the displacement, so the position of the mass, is kind of something of cosine, and the velocity goes something with the sine function. So both are bouncing back and forth and yeah, oscillating, but only without friction. So without friction, if you just displace it, it will just bounce back and forth forever, right? Until you maybe stop it. And with friction, we would have kind of a damping factor that the oscillation decreases until it's back at its equilibrium point. And we take a look at this later. But for now, this is how you can think about vector value differential equations, and also that they have this kind of solution. Okay. And another form of dynamical systems is going from continuous time, so having this function over time, to discrete time. So when you have an engineering system, you're probably measuring the system in discrete time. And then you have another way to define a dynamical system. And so at each state x at a time point k, the state at the following time point, which is k plus 1, is now given by a function of the state you're now into, right? And you also need an initial condition. So the next state is given by a function of the current state. This is similar, but not exactly the same to the idea of the rate of change being defined by the function of a state. And yeah, we can take a look at an example. So maybe this is more like everyday stuff than this ideal spring without friction. So it's your bank account. And so what the bank does for you is that the bank discretizes the time in years when they pay out your interest, right? So with now the state being a scalar, it's your money in your bank account, and R is the interest rate, which is paid out annually. Then you can describe the amount of money you have in your bank account by this equation. So the next year's amount of money depends on this year's amount of money and the interest rate. And when you start with the initial state x0 and you have maybe just an interest rate of 4%, which is very high these days, yeah, starting with $100, you can just calculate the amount of money you have next year and the year after, and so on and so forth, by multiplying the current amount of your bank account with 1.04. Good, so I think this is clear. Maybe you did this in school as well. Okay, And there are other forms of dynamical systems. So there are partial differential equations in contrast to the ordinary differential equations we talked about, where maybe your system is not only dependent on the time, but on another variable. And there are so-called integral differential equations, so where you have also so the time derivative maybe depends on the integral of something. We have delay differential equations and also functional differential equations. But this is just for you to know that there's a lot more out there, but we in this course and also in this tutorial are limited to these basic differential equations. So just maybe you're familiar with this. This is the landscape of dynamical systems. Okay. And yeah, I already talked about discrete dynamical system, and what's great about them is that we can use them to approximate the continuous dynamical systems. So it's not always that easy that you can guess, oh, well, the exponential function probably is the solution to my dynamical system. But in general, it's quite more complicated. You have a nonlinear system. Maybe you have not only your bank account, but yeah, a very large state space. And then it's easier to compute the discretized version of the dynamical system than to just calculating the analytic solution. And the basic way to do this is the forward Euler method, which we are going to take a look at. And we, just like the bank discretized the time in years, we are going to discretize the time in these delta t pieces. And then we iterating through time. And iterating is just what we did here for our bank account. So iterating time t1, 2, 3, and so forth. This is called iterating. And yeah, we can do this until we reach the final time we are interested in. And this is how we do this using the Euler method. And this, you recognize this is a discrete dynamical system. So we have this state at the next time point is the state at this time point, plus our time step and the function that defines our dynamical system. Okay. So apparently we take a look at this in a simulation. But maybe before I do this, are there any questions so far? So Simon has his hand up, but maybe this is still.
Oh yeah, sorry, that was yeah, you're right. Still had it up.
Good. So maybe probably this is a review for most of you. Okay. Then we can take a look at the simulation. Well, where is it? Here. Good. Okay, I'm sorry, this takes some time with Zoom and the record being on. Okay. Away. Okay. So there it is. You should also see this, right? If not. Okay. Good. So this is a simple MATLAB simulation of our function. So I'm going to walk you through this. Okay, so my PC is kind of slow. Good. The function we're going to simulate is this right-hand side of equation. This equals minus alpha times the variable, which is the state at the previous time step. So this is the minus alpha x linear differential equation we've already seen, and we know that this solution is the decaying exponential function. And yes, so then I can start right here. So the alpha, so the slope of our linear system, we say it's 0.5. And so we have no noise in our system. And we simulate this until a final time of 10, whatever 10 is in this system. Then the 0.1 is our time step. Yes, then we know the number of time steps we need to reach our final time 10. So for plotting, we want to know what time this actually is, and then we have the variable, so which is our state x. And I also calculate the analytic solution because we know that this is the exponential function, so we can compare them later in the plot. And the initial condition for both of them, the numeric and the analytic solution, is 1. Yeah, and then this is the iteration we do. So going through each time step, and then we calculate, this is the Euler step here. So we calculate the state of this time step equals the state of the last time step plus our time step times the right-hand side of equation, which is our function f of the state. And you can ignore this because this is for the noise. And our analytic solution is our initial condition times the exponential function with this minus alpha times the state of this time step. No, times the time at this time step, sorry. Okay. So no magic there, just equations. And we can run this. Good. And it misses the legend. So the numeric solution is the red one and the analytic the blue one. And I make this larger. So this seems to be pretty good, right? So we have our decaying exponential function, which is the blue one. And then there's some displacement for the red function, which is the numerical approximation. Okay, so this is because we have a very small time step. So delta t is 0.1. So we can just make it larger, maybe 0.5, and do this again. And we see that it's getting worse. So again, the blue one is our exponential function. We know that this is the solution. And it's not as smooth because this is also only computed for fewer time steps, right? But now the displacement between the analytic and numeric solution is larger, right? So for this to work, we need small time steps. And the smaller the time steps, the closer I am to the actual derivative. And this is why I'm closer to the analytic solution. Okay, so we can make this even worse by maybe putting a 1 here. Okay, so this seems to be pretty bad. And in fact, the Euler approximation is pretty bad. And we would prefer to use more sophisticated methods, but they are not as easy to explain. So this is why we talk about Euler's method here, which is also kind of nice because it's so simple. Okay, but what we can also do is we can change the alpha. And what happens when I change the alpha to higher values is that we have steeper decay. So the exponential decay is faster, so to say. And this makes it more complicated for the Euler step to approximate the function. And I think Simon has a question.
Yeah, in the book they said that the Euler step should be, I think, 10 times smaller than the relaxation time.
Yes.
But why is that? I didn't get that.
Yeah, we see this now.
Oh, okay.
This is what I wanted to show you. Yeah, so this getting worse and worse, right? So, and let's do 5. Okay, and now this happens. So the numerical solution or approximation is now the red curve, right? And it starts to oscillate here, and it starts to get bigger and bigger. So we have 1,500 of whatever unit this is. And the blue line here is just this very tiny, small exponential decay we saw in the previous plots. So what happens when the time step is too large compared to the rate of change of the function? So the exponential function decays very fast and the time step is very large. It's hard for the Euler step to like follow the trajectory of the actual solution, and this is what we then call numerically unstable, and this is why it starts to diverge and oscillate. And so you can calculate that this you need this rule of being, I don't know, 10 times the alpha value. But what's more important for you to know is that the Euler step gets numerically unstable, and we will talk about stability in the second part of the tutorial. And this is also why we would use more sophisticated methods which provide a better stability in your numeric simulation. So also when we talk about numeric simulation, we need some stability in our discrete dynamical system for it to work. Okay, so I think this is what we wanted to show you with the simulator. So I just kill it and hope it goes away. Good. At least for me, it's 10 past. So I hope that you're all back. I can't tell because no one has his camera on. So I just hope you're back and we continue. Good. So this part is the more advanced part. So we're talking about stability and maybe also about bifurcations. And we already discovered that in our phase plot, when our time derivative is 0, then our state is not going to change. And this is why we call it a fixed point. So it's a constant solution of our dynamical system. So that is equivalent to saying that this is a state with a 0 rate of change. And what's important is that all of your state vectors, or entries in your state vector need to be 0, because otherwise it would still change in one direction while being fixed in others, right? So this is when the rate of change of our system is totally 0, then we are in a fixed point, which is a state. And we can tell them in the phase plot by finding the 0 crossings, which is kind of easy, and we already did that. So this is again our nonlinear dynamical system, and we have this phase plot. And we can simply find the fixed point by just identifying the 0 crossing. And this also is an attractor, because every state that is at the right-hand side, so the larger state value, is driven towards this point, because here the time derivative is 0. And all states at the left-hand side, so at smaller state values, are driven to higher values, because here the time derivative is positive. And this is why we call it an attractor. But we will define an attractor in a more sophisticated way later. So what's nice about fixed point is that we can control our system, that we know in which state it's going to be in the next time points. Okay, so what I explained about stability means really asymptotic stability. And here's a mathematical definition for those of you who enjoy reading the math script. It is a fixed point which is asymptotically stable when solutions of the dynamical system that start nearby converge in time to the fixed point. Let us verify this using our nonlinear dynamical systems. So states that are nearby this fixed point are driven towards this, and we call this converge to it. So for states in this region, we are pretty sure that they, in some amount of time, are going to be in this fixed point, and once they are there, they stay there, because the rate of change is 0. But what is this with these neighboring states? So when you imagine being here, and here the rate of change is 0, then it would not necessarily converge to this fixed point, right? So it just stays here, and whatever it does here, it does here. So stability is always something that is local defined. There may be fixed points that are globally stable. That is like the linear system we already investigated. So it does not depend how far away your state is from your fixed point. At some point in time, you are going to be in this fixed point, because all forces in your system are driving your state to the fixed point. But this is not necessarily true for all dynamical systems, and especially not for nonlinear systems. Okay, so this is what the mathematicians mean by asymptotic stable. Yes, this is what I already said. So only the nearby solutions stay nearby. Okay, so the definition of a fixed point being unstable is that it is not stable in this more general sense. And we will see what this means. So nearby solutions do not necessarily stay nearby, and they even may diverge. And this is what I hinted at when I said that this does not necessarily converge to the fixed point. Okay, so this is the concept of stability. The mathematical definition, and we see how this looks like in practical examples. So what we want to know is how to tell whether a fixed point is stable or unstable, because this is really a nice thing to know about our system. Can I predict what it does in the future? Maybe converging to a stable point, or maybe just diverging and do something else, whatever it does. Good. So, and what we usually do is, even when we have a nonlinear system, we approximate it by a linear function close to our fixed point. So now our nonlinear system would be the red line, and what we simply do is like draw a linear function through the fixed point, which has, of course, the slope of the nonlinear system in this point. So the nonlinearity here can be seen as a small perturbation of a linear system, which has like a qualitatively the same behavior. And what is nice is that we only need to analyze the linear system, because this is much more easier than analyzing a nonlinear system. Okay, so with that having said, we can restrict our analysis to linear systems, and this also is a one-dimensional system. So we only have this one scalar state lambda. So I'm sorry that we switch from x to u to lambda. So the state now in this picture is called lambda. But maybe for you, this is nice about actually reading the axis label, because then you know what's going on in the plot, no matter if it's called x or u or lambda. Again, so this is a phase plot, our state lambda, and its time derivative. It's a linear function. And now if the slope of this linear system is negative, the fixed point, which is the zero crossing, is asymptotically stable. And we already analyzed this because every state here has a negative time derivative, is driven to smaller values, and any state here has a positive time derivative and is driven to higher values. So this is the mental simulation you can do in your head when you see a phase plot. Okay, what about a positive slope? Then the linear system is so the other way around, and any state that is at the right-hand side of the fixed point has now a positive rate of change. So it's going to be driven to even larger state values, so away from the fixed point. And if you are on the other side, then you have a negative rate of change. So also your state is going away from your fixed point. However, if you're exactly in this middle point, your time derivative still is zero, and you would be like fixed. So it's still a fixed point. And if your state exactly sits in this fixed point, it's not going to change. But if there's a small perturbation to the left or to the right, and saying to the left or to the right is a little bit sloppy, but in this plot, kind of it's true. So if you're a little bit perturbed, then you would just go away from your fixed point. And this is what we call an unstable fixed point. Okay, so this is when the slope is positive. So what happens now when the slope is 0? Then, yeah, this is called marginally stable. So in principle, every state here is stable. But if it is perturbed, it's not going to be driven back to its initial state, right? So it just stays in the perturbed state because this is also a fixed point. So it's not really stable, but somewhat stable. And yeah, so the 0 slope kind of is in the middle between the stable and the unstable fixed point. And yeah, we already encountered this word attractor. So we would call this fixed point an attractor because it attracts all nearby solutions. And this is what we would call a repeller, so an unstable fixed point, because if you're close to it, you would be repelled from it, except when you're sitting just inside the fixed point perfectly. Which is kind of in real engineering or physical systems impossible because you always have some noise. Okay. And then we have this weird case where kind of every state is stable, but not really stable. Okay. So maybe before we talk about the multiple dimensions, are there any questions about the one-dimensional case? So this is the case we'll mostly talk about in the lecture. Okay, seems not to be the case. Then I will just continue talking. And yeah, when we generalize it to multiple dimensions, then the system is stable or has stable fixed point if the real parts of all eigenvalues are negative. And we talk about real parts and eigenvalues in a moment, just for those who already know this. And it is an unstable fixed point, or the system is unstable, if any real part of an eigenvalue is positive. And also we have this weird case of the real part of any eigenvalue being 0. And then it's kind of this weird marginally stable thing in that direction. But other eigenvalues may have a negative or positive real part, and then the stability depends on those other eigenvalues. This is only true for linear systems, and we talk about nonlinear systems in a moment. But first, we have a short recap on eigenvalues. Sorry. Okay. So, I think this is not covered in school, so probably this is new to you. If this is the case, it's probably worth looking this up. But for now, just accept that eigenvectors, so an vector V of any matrix A are those vectors that obey this equation. So the matrix times this vector equals some scalar times this vector. So, which is kind of nice because apparently the matrix does not rotate our vector in space. It just scales it with this eigenvalue called lambda. So it's when lambda is a real number, it's just stretched in the direction it already points, but it's not going to be a completely new state. Yes, so this is why eigenvectors and eigenvalues are so important. Yeah, and this is what I always said. So just for you to know what eigenvectors and eigenvalues are, and we now take a look at why they are important for stability. So when we now have a solution to our system with multiple dimensions, remember we had this example of the spring and the mass, where our function of our state was simply a matrix multiplied by our state. So this is now the time derivative of our state vector, and the function is, in a linear system, the matrix times our state. So, and when we now naively try to solve this, we would say, well, nice, I know that in one dimension, this is simply the exponential function. So the function we talked about in the first slides, and we solved numerically using the Euler's method. And maybe I can just like put the matrix here in the exponential function. And to do this, I need to know what is the number e, so e is just a number, right, raised to a matrix. What is this? And can I do this? And apparently I can, but I can do this only if the matrix A is diagonal. So here's a two-dimensional example. So the matrix A being diagonal means that I have here this diagonal line, and all other entries in the matrix are 0. And apparently, when I have this kind of diagonal matrix, it follows that the exponential function of this matrix is just my matrix, and now with the exponential function of these lambdas. And I call them lambdas because it turns out that when I know the eigenvectors, I can diagonalize my matrix by putting the eigenvalues like on this diagonal line. And there are some limits to this. Sometimes this is not possible, but maybe just accept that in most cases we can diagonalize our matrix by putting the eigenvalues, which I can calculate in some way, on the diagonal line. And if I can do this, I can find a solution to this weird expression of the exponential function being raised to a matrix. Okay. But still, so now we have this as a solution. And why are we talking about real parts or imaginary parts? So it turns out that those eigenvalues that we can put on the diagonal line of our matrix can be complex, even if we have a totally real physical system. And then we not only need to know what is the exponential function raised to a matrix, but we also need to know what is the exponential function of an imaginary number. So when we talk about imaginary numbers, we always have the real part A plus this kind of imaginary number times our imaginary part B. So you can also think about an imaginary number as being a vector, with the real part is one entry and the imaginary part is the other entry. And then again, it's Euler. So we have now not Euler's method, but Euler's formula that tells us that having the exponential function of a complex number, so with the real part and the imaginary part, this is just the normal exponential function of our real part. And then apparently, and you need to accept this if you don't know this, that the cosine function of the imaginary part plus the imaginary number times the sinus function of the imaginary part again. And this is just a figure from Wikipedia, which shows this part of the equation. And this is just a vector that rotates around the unit plane that is spanned by the real part and the imaginary part. This may be a little bit abstract, but just accept that this gives you an oscillation, and a lot of systems are going to oscillate. But we are fine with oscillation, right? So this does not say anything about stability because this has a maximum value of 1 in the unit circle. So what's really important for us to know is the amplitude, which is given by the exponential function of the real part. So this gives you kind of the amplitude of the vector, and this gives you the rotation in this real imaginary plane, loosely spoken. And what's important for us to know is whether when this is being the function that determines our rate of change, and now a is a positive number, the rate of change would increase and increase and increase over time. So I'm probably not going to stop anywhere close to a fixed point because it's always an increasing rate of change. But when my real part, so when my a is negative, I have this nicely decaying exponential function that we have seen in the first slides. So this is why we want to have the real part to be a negative number to get this decaying exponential function and not this exploding exponential function. And then we have this oscillation in this exponential decay, but this is fine, right? So we just oscillate towards our fixed point, and this is good. So this is why the real part is so important. Okay, so maybe this is something you want to look up, or you can just accept it, but it's probably it's hard to follow right now. But that's totally fine. Okay. So this was only for nonlinear systems, and no, for linear systems, of course, and probably we have a nonlinear system. And what we're going to do now, so as stability is a local property of the fixed point, we can again linearize our system around the fixed point. So exactly the same that we did in the one-dimensional case, but now we do it in multiple dimensions. And then again, we have the eigenvalues of this linearized matrix that defines our dynamical system gives us the idea of stability. With all real parts being negative, it's stable. If any real part is positive, it's unstable. And now when we have this weird case of any real part being 0, it's undecided. So then it really depends on the nonlinearity in the system. And we cannot cover this by just taking a look at the linear system. And this is also called a non-hyperbolic, nicht Pollic, fixed point. Okay, so here's an idea, but this is only for, again, we can only plot this for one dimension, but think about this being in multiple dimensions, just imagine. So all real parts are negative, then maybe we have this kind of function and we can nicely linearize it. And then we have the positive case where we can linearize it and we get positive eigenvalues, so it's unstable. But what happens in these zero real part case, then so it may be unstable because here you see that locally we have a zero slope, but when we take a look at the non-linearity of the system, we find that there is maybe some, in this case, unstable fixed point. Here it's a stable one, and here it's kind of this weird marginal stable one. Okay. And this was all really abstract, and I tried to give you an example so that you get a feeling why this is useful and why scientists do this a lot. This is also, so it's nice for you to understand, but in the course we will focus more on the conceptual understanding of one-dimensional, maybe a few times multiple dimensional dynamical systems in the first lectures. So it's not a big problem if you do not understand like the calculus and so on. Just get a feeling of what we're doing here. So you probably all know a pendulum, like maybe your grandmother's clock. And this is a nonlinear dynamical system. And again, like having the spring, you need to believe me that this gives you the acceleration of your system. This has to do something with the force that is pulling the mass down, and due to the because it's fixed here, we only care about the force that points like in this swinging direction, and we get this with this term using the sinus of theta, and theta is the angle at which the pendulum is displaced from its equilibrium point, which is again this dashed line here. And because it's more fun, we also add some friction to our acceleration, and in physics, friction always depends on the velocity. So this is why we have delta times omega. And now I do not write x and v for position and velocity because we have this angular rotation. So instead of the position, we care about the angle, and instead of the velocity, we care about the angular velocity. So it's not the position that changes, but it's the angle that changes, right? So these are the two differential equations we can write down. Again, the first one is trivial. So the rate of change of my angle theta is just omega, and then we have where really the magic or the physics happens. This is the acceleration. So the force that makes your system oscillate. And what's nice about the pendulum is that we already know the fixed points. So we do not need to calculate them for this example. And of course, in our fixed points, the velocity should be zero, right? So you're not moving. And we know that this is, of course, true for this equilibrium position. So when your pendulum just hangs down. But when you have an inverted pendulum, so maybe it's like this just points upwards. So I can do a really bad drawing of this. So if this points upwards and here, oh well, no, here is your mass, right? then it's also stable. Okay. So maybe you are able to find the correct angle that this stays here. Yes. So, and this is at an angle of pi. So, like just from here to there, right? Okay. So what we now do is we linearize around these two fixed points to find this matrix A, to analyze the eigenvalues of this matrix, and then to say whether it's a stable or an unstable fixed point. Okay. Good. So, and we do this after some calculus, because so you can write this in a matrix. So you can't write this in a matrix right now, but you need to linearize it. And for those of you who know this, we would compute the Jacobian of this function, which basically is the derivative for each variable we have in our system. And we compute the Jacobian for both fixed points, so for 0, 0 and for pi 0. And then we plug the fixed points in the Jacobian, and then we get two matrices, so two linearizations around the first fixed point and the second fixed point. And so for now, just accept that this is the matrix that gives us our dynamics for the pendulum hanging down. And this is the matrix that defines our dynamical system for this inverted pendulum case. And they pretty much look the same, but there's one important difference, and this is the minus sign here. Okay, so this is the Jacobian and our fixed points plugged in for those of you who are familiar with these concepts. And what we find now when we compute the eigenvalues, and we did not talk about how to compute them, but you can compute them maybe by hand or just using MATLAB or whatever. And then we find that for this pendulum hanging down, that both eigenvalues have a negative real part. So in fact, they also have an imaginary part, which gives us this nice oscillation. But we also have a negative real part, so that the amplitude of our oscillation decays over time until the fixed point is reached, which is stable, the stable case of the pendulum just hanging down. And if there's no damping, then we would not have this nicely decaying amplitude, because it would just oscillate back and forth forever, right? So there's really no fixed point. So we need the damping here. Okay, what about the inverted pendulum? And here we find that there's one positive and one negative real part of an eigenvalue. So, and this gives us that it's an unstable fixed point. And this is what we already knew, right? So we have a stable fixed point here when the pendulum is hanging down, but when you have it inverted, then it's a really unstable system. And yeah, this is what the eigenvalues tells us. So this is trivial for an example where we simply know the solution, but we would do exactly the same for any other unfamiliar system. Okay. Good. So this is all I have to say about stability and linearization. And we could now talk about bifurcations. And yeah, probably I will just continue, because we can still yeah, have some time from the exercise session, except for you being too exhausted or having too many questions. So maybe this is the point to give me some feedback or ask some questions.